Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is a continuation of our study of integration and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the introduction to integration prior to watching this video. In this video, we will be discussing even and odd functions, the average value of a function, and the substitution rule. Remember from your algebra lessons that an even function is one that is symmetric across the y-axis, where f of negative x equals f of x. Examples of even functions are f of x is equal to x to the n, where n is an even integer. The graph gives the example of the parabola formed by f of x is equal to x squared. An odd function is one that is symmetric across the origin, or where f of negative x equals negative f of x. Examples of odd functions include f of x is equal to x to the n, where n is an odd integer. The graph here is the example f of x is equal to x cubed. If we were to look at the same two graphs and shade the area between the function and the x-axis on the interval -1, 1, we can see that the shaded areas to the left and right of the y-axis are equal, with the even function appearing above the x-axis and the odd function on the opposite side of the x-axis. From this, we can derive the following theorem. Let a be a positive real number, and let f be an integratable function from -a to +a. If f is even, then the integral from -a to a f of x dx equals 2 times the integral from 0 to a of f of x dx. If f is odd, then the integral from -a to a of f of x dx equals 0. As an example, let's use the rules of symmetry to evaluate the integral from -2 to 2 of x to the 8th dx. The theorem for even functions states that it is equal to 2 times the integral from 0 to 2 of x to the 8th dx. The antiderivative of x to the 8th is x to the 9th over 9, and we take that from 0 to 2. We get 2 times the quantity of 2 to the 9th over 9 minus 0 to the 9th over 9, or 2 times 512 over 9, which simplifies to 1024 over 9, or approximately 133.78 units of measure taken to 2 decimal places. The average value theorem states that a function that is continuous on an interval AB will have an average value. We can think of an average value the same way we do the average of a set of data points. For a function, we use the overscore f, sometimes called f bar, to indicate the average value of a function. Observing the graph to the right, if f bar is an average value on the interval AB, then f times b minus a is equal to the integral from a to b of f of x dx. The left side of the equation is simply the area of the box bounded vertically by the x-axis and the average value of f, and bounded horizontally by a and b. The right side of the equation, the integral from a to b, is the area under the curved segment. From this, we derive the average value of a function as 1 over b minus a times the integral from a to b of f of x dx. The mean value theorem for integrals derives from the average value and states that if f is continuous on AB, then there is at least one c on the interval AB such that f of c equals the average value of f on AB. This theorem states the following. Let f be continuous on the interval AB. There exists a c on AB such that f of c equals the average value f, which equals 1 over b minus a times the integral from a to b of f of x dx. As an example, let's find the average value of the following function. F of x is equal to x squared minus 2x plus 2 on the interval from 1 to 3. F of c equals 1 over 3 minus 1 times the integral from 1 to 3 of x squared minus 2x plus 2 dx. We can simplify the fraction to 1 over 2. Then take the integral to get x cubed over 3 minus x squared plus 2x evaluated from 1 to 3. This equals 1/2 times the quantity of 3 to the third over 3 minus 3 squared plus 2 times 3 minus the quantity of 1 cubed over 3 minus 1 squared plus 2 times 1. Simplifying, we get 1/2 times the quantity of 9 minus 9 plus 6 minus the quantity of 1/3 minus 1 plus 2. Simplifying further, we get 1/2 times the quantity of 6 minus 4 over 3, or 1/2 times 14 over 3, which gives us our final answer, 7 over 3. The chain rule is a useful tool in finding derivatives of composite functions. Using this tool in reverse, the antiderivative of some composite functions may be found. The theorem states that we let u equal g of x, where g is differentiable on an interval, and let f be continuous on the corresponding range of g. On that interval, the integral of f of g of x times g prime of x dx equals the integral of f of u du. As an example, let's find the indefinite integral of 2x times the quantity of x squared plus 1 to the third power dx. Here we let u equal x squared plus 1. Du is then 2x dx. We now substitute these values to get the integral of u cubed du. This is a simpler integral to solve as u to the fourth over 4 plus c. Substitute back in for u to get the final answer, the quantity of x squared plus 1 to the fourth power over 4 plus c. Let's look at another example, this time where the integrand is not set up so nicely. Find the integral of x to the fourth times the quantity of x to the fifth plus 6 to the ninth power dx. Again, we set u equal to the inner part of the composite function, x to the fifth plus 6. Du will then be 5x to the fourth dx. Since the 5 is not part of the original integrand, but the x to the fourth is, we solve this part for x to the fourth dx, which is equal to 1 over 5 du. Now we substitute to get the integral of u to the ninth times 1/5 du. Since 1 over 5 is a constant, it can be moved to the outside. When we take the integral, we get 1/5 times u to the 10th over 10 plus c. When we substitute back in for u and multiply the 1/5, we get our final answer, x to the 5th plus 6 to the 10th power over 50 plus c. The substitution rule also works for definite integrals. Let u equal g of x, where g prime is continuous on AB, and let f be continuous on the range of g. Then the integral from a to b of f of g of x times g prime of x dx equals the integral from g of a to g of b of f of u du. As an example, let's evaluate the integral from 0 to 1 of 2e to the 2x dx. First, let u equal 2x, which would make du equal to dx. Since gx is 2x, that would make g of 0, 0, and g of 1, 2. Then we can evaluate the integral from 0 to 2 of e to the u du. The antiderivative of e to the u is e to the u, which we then evaluate from 0 to 2, or e squared minus e to the 0, which simplifies to e squared minus 1, or approximately 6.389 units. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.